Hello everyone, welcome back to FUSION22, and if you're just joining us online, then welcome to FUSION22 from London. We are so glad you are watching from wherever you are around the world, and we'd really encourage you to join in the online chat and ask questions in the Q&A, as well as check out our virtual exhibitor booths. Now, this session is all about the diversity of technical approaches to fusion, something that we touched on a lot earlier on. And encouraging new ideas and approaches in fusion is critical to remaining innovative. Now, joining me to explore this issue is Scott Su, the lead fusion coordinator at the US Department of Energy. Scott advises the Undersecretary for Science and Innovation and is spearheading efforts to accelerate fusion energy R&D and also the commercialization in partnership with private energy companies. Scott isn't here with us today. He's actually joining us from the American Physical Society's annual plasma meeting in Spokane, Washington, where it's 6 a.m. in the morning. So we're so grateful you can join us, Scott, here in London and online. Welcome, Scott. Let's just try and sort out Scott's sound. He can obviously hear us. Hopefully we'll be able to hear him. Scott, earlier we heard about the fantastic progress that is being made around the world. And what I think was so striking to everyone was the diversity of machine designs and even the fuels that are being used. Can you just help us explain this and help us make sense of this zoo of approaches to fusion?
Yes, muted now. I hope you can hear me.
Yes, we can, Scott.
Okay, well, thank you, Valerie. It is early, but I'm so glad to be here with all of you, and thank you for the invitation. Yes, it's been a great interest and passion of mine to explain the zoology of fusion approaches to a broader audience. Fundamentally, we're talking about they're all doing the same thing, right? They're trying to generate enough fusion energy released to power, for example, a steam turbine to create power in like a fusion power plant. And fundamentally, they're trying to do the same thing. They're trying to bring fusion fuel to a certain density, a certain temperature, and for long enough time such that the energy released is greater than the energy invested. That's what we're here to do.
And so we heard about earlier about magnetic confinement fusion, inertial confinement fusion, and magneto-inertial confusion. There we go, confusion. A slip of the tongue there. Again, can you just sort of talk a bit more, elaborate on a bit more on those three approaches?
Yes, indeed. Thank you. And I've made that same gaffe myself. Yeah, there are three main approaches, although there are variants even beyond those three. However, for magnetic confinement, the first one, you're using a very strong magnetic field to hold the fuel there. And in that case, the density is, and you need to hold it there longer. Then you have inertial confinement, which is on the far end of the spectrum, very dense, and you're holding it there for a very short amount of time. And then finally, you have something in the middle, where you're using both a magnetic field and a compression to go into an intermediate scale. And sorry if I'm pausing a bit. I hear my own echo, and there's a delay.
That's quite all right, Scott. So we're not experiencing any sound issues with you. We're hearing you loud and clear. But even within each of these three categories, there still seems to be this great diversity. Why is that? I mean, presumably there are trade-offs. Could you just expand a bit more about the kind of trade-offs within each of these approaches?
Yes, absolutely. I would like to emphasize there's no silver bullet. All the fusion concepts are making some very calculated choices to go after certain advantages, but nothing comes for free, right? Something else may be harder because of it. Within magnetic confinement fusion, there are many different magnetic field configurations. And this is what leads to things like the tokamak, the stellarator, the field reverse configuration, and there's many more. For example, the tokamak would be like JET in the UK. The trade-off in magnetic confinement fusion is the degree of control you exert using the magnetic field, and these can come at different strengths and in different shapes and topologies. And so that's that's you're making. And on the other end of the equation is how good your plasma stability and confinement is based on your choice of magnetic field. So if you have less magnetic field strength or maybe a simpler topology, well, that's great for your simplicity of your design and the lower cost. However, the plasma control may suffer and vice versa. So that's the choice in magnetic confinement fusion. And similarly for magneto-inertial and for inertial confinement, you also have trade-offs to make.
Earlier on, in one of the sessions we had earlier on, I think it was Tony Donny from Eurofusion asked about tritium, and clearly there are huge costs that come with building a tritium infrastructure. You know, are there any clever ways to get around that we're seeing?
Yeah, great question. And the tritium infrastructure and the need to breed tritium is indeed, you know, adds a lot of difficulty and complexity to the system. And this is why I think that despite the very greater physics challenge of getting to higher temperatures and pressures, many companies out there are pursuing advanced fuels, what we call advanced fuels. Things like deuterium fusion or deuterium helium-3, or maybe the holy grail of them all, proton-boron 11. And these fuels do not need tritium as an input fuel, and so you would have a great advantage.
Another question that came up online concerned neutron damage to the vessels, to the fusion vessels. You know, what about that? Are there any sort of clever workarounds there so that we, you know, one way to would be to look for neutron-tolerant steels and to make them. But what about any clever workarounds there that you're seeing?
Yes, indeed. In fact, there's a couple ways, right? First of all, the advanced fuels would also have either far fewer energetic neutrons or very little at all, and so that's one great advantage. And your materials don't suffer as much, and in fact, you may have life of plant type materials in that case. But for deuterium-tritium fusion, where there is a high energy neutron, people are looking at a variety of concepts. One of the ones that intrigues me a lot are pure liquid first walls, as an example. If you can manage to arrange a thick liquid, flowing liquid, if you will, then you can stop most of the neutron damage and put most of your materials behind that liquid. And there are certain concepts that are more amenable to this than others.
Yeah, what about these liquid walls? I mean, that sounds, as a newcomer to fusion, that sounds a pretty big challenge.
Yes, indeed. And I mentioned that some concepts are more amenable. Magnetic confinement fusion, unfortunately, has a little bit more challenge in using thick liquid walls because these liquids tend to be slightly or even very conductive. And so the magnetic field, time-changing magnetic field, can be disruptive to flowing conductive liquids. The conductive liquids are best suited for perhaps inertial schemes or magneto-inertial schemes where the plasma is held very far from the wall at peak fusion.
Yeah. when you look at the fusion devices that are around the world, I think the International Atomic Energy Authority lists about 130 that are under construction or are running or being planned. And tokamaks seem to dominate that list of 130. But there now seems to be a greater diversity than ever before, particularly among the startups and the private fusion companies. What are your, how has this diversity arisen?
Yeah, indeed. Much of controlled fusion's research has focused on the tokamak because it became the best performing concept. But in the first 10, 20 years of controlled fusion research, people tried all sorts of approaches to heat that plasma fuel. And it continued onward. However, when the tokamak became the best performing concept, I think attention focused on the tokamak and accelerated its development through the 1980s and 1990s. People always stayed interested in the other concepts because of their advantages, right? We talked about earlier, people were willing to make those trade-offs to continue pursuing those advantages. Today, I think the interest has returned because some of these concepts seemingly reached dead ends about 20, 30 years ago. That was possibly due to a lesser understanding of the science, also possibly due to less mature technology for heating and assembling those systems. And so with the scientific maturity and other enabling technologies today, many groups think it's worth taking another look at those concepts.
Okay, great. Just a reminder to our audience online, do submit your questions. Some of the questions are starting to come in. We would love to hear some more questions from you, and we'll put them to Scott once we've gone through my list of questions too. Is there a danger, Scott, that this diversity of approaches could be interpreted by investors or by politicians as a sign that fusion somehow lacks direction?
I don't think so. I mean, I think, of course, people may wonder that, but I'd like to, point to lots of reasons for keeping multiple ideas on the table. Firstly, diversification and embracing of a spectrum of risk ensures better overall chances of success for commercial fusion. And furthermore, there's a greater chance that fusion, if it pursues multiple approaches, could benefit from other fields and other new breakthroughs in technology. Just some examples. Advances can come from many directions. High temperature superconductors is maybe the best example today for fusion, but there's a whole host of others that are enabling the other concepts. For example, different ways to control your plasma and feedback control. These require electronic advancements, better heating technologies, better lasers or advanced manufacturing, and the list goes on. So many of the concepts will benefit from some, but not all of these types of breakthroughs. I would also say that different approaches have different possible energy markets that they're well suited for. For example, different sized units for electricity generation, higher temperature heat possibly for industrial uses of heat, or even space propulsion and other non-energy applications. So a very diverse range of fusion can enable these different markets.
I'm really glad you brought up industrial heat there because we had a talk at the start of the day about the need to decarbonize our energy sources. And I've been reminded recently that only 22% of our energy use goes in towards electricity, and a big proportion of the remainder is in industrial heat. How can fusion, what are the concepts that could help with industrial heat?
Yeah, so again, like I said, industrial heat applications require a range of temperatures. And And right now, fusion is limited not by how much heat it can generate. It can generate arbitrary amounts of heat, but it's the material that limits the temperature that you can access that heat. So DT fusion, of course, creates its energy it traps its energy in a blanket. So fundamentally, it does provide heat. And that heat can be used to produce electricity, or it could be used directly for these processes. In fact, I like to say that fusion is a source of primary carbon-free energy, period, and not only electricity.
That's fascinating. I mean, just to single out one company that I work with as part of the fusion cluster, and that's General Fusion. And I think what's really interesting about their approach is they're already at this early stage. They're working with the first adopters. They're working with those industrial heat companies, or the companies that will be big users of industrial heat, as well as power companies. And those discussions are informing the design of the machine that they are building. I think that's really sort of fascinating seeing that as well. People in fusion, particularly in the US, I hear you talk a lot about this Kitty Hawk moment for fusion, when a fusion energy company or a lab somewhere reaches that energy break-even point where you're generating more energy than you put in. What do you think is then going to happen to the diversity? Will it be like that moment you mentioned in the 60s where everyone downscaled to tokamaks? Do you think history might repeat itself once we reach break-even?
I personally don't think so, and of course it's hard to predict exactly what will happen, but I think that moment will be a rising tide for all approaches. A couple reasons. Back in the 60s, I think people were not necessarily paying direct attention to commercialization of fusion. They were still trying to solve the scientific challenges. Today, with a focus on a commercially viable system, I think the break-even will only redouble people's efforts based on their chosen commercialization paths. I do think that when fusion science and technology reaches a sufficiently high level of maturity, the private sector will be willing to invest very large amounts of capital for the increasing promise of very large returns, right? Good old capitalism. And I think we're starting to see signs of this today with the $5 billion of private money invested. I think that break-even might just break open the dam of capital investments.
Well, let's hope so. I mean, you mentioned earlier that fusion, this diversity of ideas that we have in fusion, means that we can bring in ideas from other industries. Are there any industries or other sectors that you think we should be looking at in particular to provide new ideas that will really sort of help us progress fusion?
Yeah, so I think the companies are doing a very good job of this already. And I mentioned earlier a couple of things, but I'll mention a few more. One is like AI and machine learning. Right, I think fusion is starting to take advantage of that, but I think we have a lot more to do there to take full advantage of it. That's just one example.
Okay. And diversity of ideas comes from a diversity of people. We want people from all walks of life to come and join us and work in fusion. In your view, how do we in fusion attract that diverse workforce?
Yeah, that's a very important and a tough challenge. I think we have to look at the entire pipeline. There are short-term and long-term actions all of us collectively need to take. And I think this is a great area for international collaboration as well. I think for younger students, we need to just get them excited about science and energy, and so they will have a focus on this as they choose what to learn and what to do. I think later on in the pipeline, we need more than just PhD scientists. We need people who have just a good STEM background and have training to build things, to work with hardware, to retrain workers that have been displaced by the energy transition. So this is very important thing we have to do.
Mm. And are there any specific initiatives in the US at the moment that are really addressing this issue in fusion?
Yeah, I'll give one example. At the Princeton Plasma Physics Lab, and I suspect they may even have gotten some inspiration from what you might be doing in the UK, is there's an apprenticeship program that reaches out to local community colleges and offers paid internships to work on experiments, to work on fusion experiments. And then at the end of their internship, they may be offered a full job at Princeton Plasma Physics Lab. I would love to see programs like that reproduced at all the major fusion institutions around the country. That's one example.
Mm. And just another shout out for an initiative in the UK that ran recently. There was a fusion industry school, and that was for people working in industry who were newcomers to fusion, and this really gave them a grounding in fusion, some of the science and some of the challenges and some of the issues. And that was very successful. And it would be great if we could see initiatives like that rolled out across the globe. To put you on the spot then, where do you think fusion will be in 10 years' time?
Yes, again, it's always hard to say what will happen, but I'll give you my personal perspective. I believe in 10 years, we have a real chance of having a fusion pilot plant under construction or possibly even in operation. To be clear, this will not be easy. This will take a substantial amount of further research and development and may require even a few more breakthroughs that we don't yet know about today. But that's why we want to put ourselves in the best position to benefit from such breakthroughs.
Okay, fantastic. Thank you, Scott. While we've been talking, we've had a few questions that have come in from our online audience. I'll pick up on one from Alf Cohen-Seaman. I'm not sure where Alf is watching from. Alf asks, do you consider lithium and lithium usage in rechargeable batteries as problematic competition for fusion? Will it drive up the price of lithium and make it therefore more expensive for fusion?
Yes, that's possible, but I guess I would like to point out that fusion, even if it grows to be a big fraction of the overall global energy system, each fusion plant still uses a relatively small amount of lithium compared to what's needed, if for a worldwide electrical vehicle fleet. So I think it'll be a complex balance, but it's not like fusion will be the dominant lithium market. And of course, I'll just caveat, I'm not the expert and have not looked into the detailed numbers. But it is something worth paying attention to, but I don't think it'll necessarily be the dominant market for lithium.
Okay, great, thank you. Well, let's open up questions to the floor. We have some roving microphones, so Scott, you will be able to hear the questions loud and clear. Does anyone have a question for Scott? What if we take, there's one at the back there, first of all. If you could stand up and introduce yourself, Nick.
Hi there, Nick Walkden, Fraser Nash. Hi, Scott. So my question is about the diversity of ideas, and how do you, in your view, how do you maintain that diversity not in the current generation of fusion developers who are looking at pilot plants in, say, 10 years, but in the generation of startups that might need to happen within that next 10 years so that you have a thriving system of innovation cycles that aren't going to take 10, 15 years and that you can do a rapid roll-up? How do you make sure that there is enough diversity in the landscape that you can, I guess, keep the innovation coming, keep the innovation flowing as people start to do bigger things that take longer times?
Yes, that's a very good question. And the public investment in fusion, I think, should have a role in that, right? And for the longer term vision and to make sure we're ready to take advantage of advances. I guess I might, over here in the United States, we look at our Office of Nuclear Energy for good models of how they support different technologies, right? I mean, right now in the era of advanced nuclear reactor development, our Office of Nuclear Energy is not, they're not developing their own single advanced reactor design, but they are supporting a real diversity of designs led by the private industry. But yet they are supporting the R&D needed for continued advances in nuclear reactors. I think the fusion public programs can do a similar thing.
Okay. Thank you, Scott. You mentioned conventional nuclear reactors here. We have a question online from John Carr, who asks, what real advantage does fusion have over fission? Can a fusion reactor ever be more economical than a fission reactor? And surely fusion is more complicated for the same sort of power output that you would get. So a multi-part question there.
Yeah, that's a great question. I'm sure most people have heard, right, the two main advantages of fusion, I would say, are it doesn't need special nuclear materials, fissionable materials, which is probably the main reason it is so heavily regulated. It also does not produce long-lived radioactive waste, right? That's another reason that nuclear faces headwinds. Actually, there's a third, which is the fusion does not have a risk of runaway reactions and meltdown, right? And the concerns of public safety. So those three are the really main reasons that people are excited about fusion. Now, whether it can ultimately be more economical or not, I think that remains to be seen, right? We hope it can. People who are doing cost estimates, projected cost estimates of steps, feel that fusion has a chance of being competitive even in today's markets, but it does remain to be seen.
Okay, thank you. Let's come back to the room. There are a few more hands near the front. Nope, just wait for the microphone.
Thank you. I'm Lilia from Shell Ventures. You touched base briefly on process heat. So my question is the following. When fusion reaches commercial scale and obviously maturity, will there be room for advanced SMRs, so fission modular reactors?
I think so. Again, I go back to what I said about diversity of fusion and being able to access different markets. And I think similarly, small modular reactors for fission may be able to access some markets that fusion may have a tough time doing. For example, right now, fusion is easier when it's bigger, right? I think most people are fairly hopeful that fusion can succeed at the many hundreds of megawatt electric or larger scale. The question there will be cost. Whether fusion can succeed at the less than 100 megawatt electric scale, I think remains to be seen, and that has to do with fusion. Whereas for fission, you can go to arbitrarily small unit size.
Thank you, Scott. Let's take another question from the room. There are lots of questions coming in online as well, which is fantastic. I think there were more questions over here, weren't there? I saw some hands going up. If we could just get a microphone over here. Sorry, I'm making everybody run.
William Morris, UKAEA. On the industrial heat question, do you think there's any intervention needed to encourage processes which work for industrial heat, or do you think the market will do it itself? I speak to you because you're on the US DOE, so you might have a view on that.
Well, I think the greatest invention would be a low activation material that can operate at higher temperatures, to go above 1,000 Celsius, for example. That would be a great enabler.
That's interesting. We've had an online question come in from Darlene Temple, and it was, what areas do you think are likely to have the biggest wins for fusion in the near term? Do we need an advance in plasma physics? Do we need an advance in materials? Do we need an advance in magnets or something else? Perhaps you just touched on it. Perhaps you just gave your answer there.
Yeah, I think we need to pursue parallel tracks, right? I think we need pushing as hard as we can going down the road we're going down, which is continuing to advance all those areas. I do think the plasma physics is maybe under talked about right now. Getting to a high enough energy gain for most of the concepts will still involve quite a bit of work. But like I said earlier, there could be unanticipated breakthroughs from other fields, and I think the fusion researchers should stay vigilant and be very open to trying things.
Okay, thank you. We have a question about helium-3, one of those advanced fuels. And do you think at a certain point in the future we will have unlimited access to helium-3 in the quantities that we would need for fusion?
I think it's possible, yes. You hear already a lot of talk about, mining the moon as one example. I often joke that maybe we'll actually have helium mining on the moon for fusion. It's not out of the question within, say, 10 years. I also think in the longer run, if we can do D-helium-3 fusion, it's very likely we can do DD fusion. And with DD fusion, you can breed the helium-3.
Okay, that's yeah. Thank you for that. I've always been quite fascinated by this idea of getting your fuel from the moon, and I can't really see the commercial pathway there. But perhaps with space launches decreasing in price all the time, then that may open up. What about other questions in the room? There's one right at the back. I think it's Richard.
Hi, Scott. Richard Pearson, Kyoto Fusioneering. What does success look like in 5 years, 10 years, and 20 years' time?
Yeah, thanks, Richard. Well, in 5 years, I would say I hope we can have one or more quite credible fusion pilot plant preliminary designs. As you know, the US DOE just put out a funding opportunity announcement for a milestone-based program, the private sector here in the United States. And that's what we're after, our pilot plant designs, either on a 5 or 10 year time scale. In 10 years, we hope to have pilot plants that are going to really demonstrate commercial viability or get us to commercial viability. And in 20 years, we hope to be rapidly deploying fusion systems.
Okay. Let's take another question from our virtual audience. Simon Keynes was watching you testify to the US Congress recently and encouraging government support for fusion. What support do you think what support can other governments give to the fledgling fusion industry that doesn't compete or conflict with private investments? So I think this is a question not what US government can do, but what could other governments be doing to support the fusion industry?
Yeah, great question. I guess from my vantage point, it seems like most of the other governments are still in the mold of a very strong public program. That is, if they have a fusion program at all. I do think there's a shift toward paying attention to the private industry, and I think it's natural that that will happen as more capital comes into any single government's fusion efforts. I think even here in the United States, we're still trying to perfect what we want to do and how to do it. But I think fundamentally the government's role should be to be an enabler for the private industry, right? To support the really tough early stage research challenges, to help prepare the path to commercialization, to think about market assistance as needed, because it will be very challenging for the first of a fusion plant to be competitive on the commercial markets.
Okay, thank you. Another question that's come in from our virtual audience. We may have been a bit guilty of some jargon slipping in here. Can you explain what a milestone-based program is for an international audience, and why the Department of Energy is moving forward in this way, and should it be a model for other countries?
Yeah, thank you for that question, and sorry about the jargon. The milestone-based program is been advocated for by the fusion in the United States for several years. The inspiration comes from NASA, actually, here in the US. There was a program called the Commercial Orbital Transportation, or COTS for short. This was a program that actually helped enable SpaceX with their early development of a reusable launch vehicle to low Earth orbit. And the point of the milestone-based program is to to establish a partnership with private industry that is friendly from, say, property terms, from reduced administrative burdens, and for the private industry that's willing to take on a large part of the financial risk. So in this program, the private company is expected to list a set of milestones toward a fusion pilot plant. And if they meet these milestones, which are negotiated with the US government, then the US government will reimburse them a fixed amount. And so this signifies commitment on the US government's part on their development path to get to a fusion pilot plant. And the hope is that it will bring investor confidence and unlock even greater amounts of private capital.
Okay, thank you, Scott.
And I'll just also add, that in the NASA case, that investment of, I think it was $800 million of US federal money actually led to two different private companies with new low Earth orbit launch capability. And for reference, I think it would have taken, I think by NASA's own estimate, it would have taken maybe nearly 10 times that amount of money if they were to have done it all.
Great, thank you. Any more questions in the room for Scott? I think you've really covered everything so clearly, Scott. So we have, so I think that there's more concern about skills gaps. And Dan Bissett points out that the nuclear skills gap in the UK is very much a live issue. And how can we avoid this in fusion to ensure that it's an attractive sector of choice for the next generation compared to other industries? You talked earlier about STEM programs.
Yes, we are interested in thinking about fusion dedicated programs throughout the pipeline. For those of you who may have listened in or read about the White House event in fusion back in March, you probably will have heard there's a strong appetite to really focus on a fusion industry for the future, or to build a fusion industry for the future. Unfortunately, I don't have any real specific things to share about it, but it's on my list of priorities to get some programs going. Now, DOE, of course, has kind of agency-wide programs that are trying to build diverse STEM workforces for the energy transition, but we really want to look at fusion-specific programs. And I think I would love to, collaborate with partners, international partners, on these things.
In one of our sessions earlier, Carly Anderson gave us a fantastic story about her mother being converted to nuclear power after visiting a nuclear power station, which I thought was just a sort of really sort of wonderful example. Hopefully we haven't lost Scott completely. Scott, can you still hear us? We've lost your video.
Yes, I can hear you.
Okay, great. That's great. I think we've probably got time for one more question from the audience. Does anyone have a burning question for Scott while his internet is holding up? So we have one here. Great, thank you.
Thank you, Scott. Giuseppe from Hexagon Energy Transition Ventures. A question regards the supply chain in the view of a commercial development of fusion. What do you think could be the critical parts of the supply chain? I'm thinking, for example, to the production of deuterium or to the superconductivity materials. What's your view on that?
Thank you for the question. Yes, the supply chain is also one of the topics on my to-do list, and again, also a very good topic for international cooperation. I would say I don't know that a single thing is jumping out at me, but you mentioned some very important ones. I do think that the fuel supply, startup tritium is an issue possibly, and enriched lithium-6 for the blanket is a potential issue, and also rare earths and rare metals for structural materials and magnets, and even electronic components. So there is a long list, and we are going to work on building, making a more comprehensive assessment of this.
And Scott, what about the CO2 emissions expected from the fuel production cycle or the supply chain in more general? Is that something that that you think about, that you're concerned about?
Yes, definitely. We like to. I think we should all look at life cycle emissions as a metric for pursuing different energy technologies. And fortunately, I think we will benefit from advances in other areas in decarbonizing the supply chain. But as we all know, we need to decarbonize the grid as a first step, I think, to enabling the decarbonization of many other things.
Okay, great, thank you. We're coming towards the end of our time. I am relieved that our internet connection with Scott has held up. I had a few little wobbles and jitters earlier on. But Scott, I just wanted to say it's been a huge pleasure to talk to you. Thank you so much for joining us so early in the morning for you. And thank you for answering all our questions. Please show your appreciation to Scott Shue. Thank you.